In this lecture, we shall be starting the discussion on fault modeling. So, if you recall, we discussed in the last lecture that fault modeling is one very important step that we should do at the very beginning before we go through the other steps like test generation, fault simulation, etc. Okay. So, the topic of this lecture is fault modeling. So, let us start with the basic motivation once more, that why we need fault models. So, we mentioned in the last lecture that the number of physical defects in a chip can be too many. So, you really cannot count how many physical defects can be there in a chip, because most of the parameters are continuous in nature and there can be infinitely possible values. So, you cannot test the circuit against all possible values of the parameters. Okay. So, it is difficult, I should not say difficult, it is impossible to count and analyze all possible faults. So, because of this, we do some kind of an abstraction. We abstract the defects and define some so called logical fault models. So, if we do this, the advantage that we get is the number of faults to be considered can be drastically reduced. We shall see some examples which will support this statement. And if we can reduce the number of faults, the subsequent steps of test generation and fault simulation becomes that much easier. Okay? And if we can count the number of faults, then we can also compute the value of fault coverage. We can analyze a circuit with respect to testability, that how many of faults are getting detected, which are the faults which are not so easy to detect, and so on. Okay. So, we shall be discussing a few of the fault models which are very important. There are many other fault models as well, just you should remember. So, we shall be discussing some fault models at the functional and structural levels. So, we start with a functional level fault model. So, functional level fault model means the circuit that we are trying to test, we have the description of the circuit given at the functional level. What do you mean by functional level? Functional level is sometimes also called register transfer level or RTL level. Here the basic building blocks of the circuits are not gates, but slightly higher. We talk about registers, adders, multipliers, multiplexers, and so on. So, we have a circuit at that level, that is something which we called functional level. And the point to note is that fault models that are defined at the functional level, they are very specific to blocks. Like for a multiplexer, I will have some fault model, for an adder I will have a different fault model. They are not general, they will be very specific to the blocks that are being used. But let us say for a multiplexer, if you have a strategy that will be very efficient, I will take an example for a multiplexer. You can see that the test set can also be generated fairly directly. Okay? This we shall be seeing. So, this 4 to 1 multiplexer I shall be taking as an example, where there are 4 data inputs, 2 select inputs and 1 output. So, let us take this example. So, you look at the multiplexer schematic diagram here. The 4 inputs are here A0 to A3, select lines S0 and S1, and the output is F. The corresponding truth table is shown here. Well, here the assumption is that S0 S1, if it is 0 0, then we are selecting A0. Okay? 0 0 means A0 is getting selected. If it is 0 1, 0 1, that means S1 is 0, S0 is 1, S0 is the least significant bit, 0 1, then A1 is selected. If it is 1 0, S1 is 1, S0 is 0, then A2 is selected, and if it is 1 1, then A3 is selected. So, with respect to the test generation, what we do? You see, we apply the 4 possible values of the select lines 0 0, 0 1, 1 0 and 1 1. Now, we know when I apply 0 0, this A0 is supposed to be selected. So, we apply both condition. If A0 is 0, then the output is supposed to be 0. If A0 is 1, output is supposed to be 1. Okay? But we also do something more, like we are talking about a functional fault model. Like we know how a multiplexer works. Okay? If S0 S1 is 0 0, A0 is supposed to be selected. But because of a fault at the functional level, what you may say that, well, because of some fault, instead of A0, maybe some other input is getting selected, maybe A1, maybe A2, maybe A3. So, just to safeguard against that, what I do, you see, when A0 is 0, we are applying reverse values in A1, A2 or A3. So that if accidentally any other of them are getting selected, so the output will not be 0, it will become 1 and it can be detected. Similarly, for A0, when it is 1, then we are applying reverse values in the others. Same thing for the other combinations. For 0 1, this A1 is made 0 once and 1, and the other inputs are at the reverse value 1 1 1 or 0 0 0. For 1 0, A2 same, and for 1 1, A3. So, you see at the multiplexer, just looking at how a multiplexer works functional level, we require 8 test vectors only. But if you look at the total number of inputs, there were 6. With respect to the truth table, 2 to the power 6 is 64. So, instead of applying 64 possible inputs, we need to apply only 8 inputs to test the functional behavior of a multiplexer, right. This is the basic idea. We need not have to apply all possible inputs. We have to understand the functional behavior of the circuit we want to test. With respect to that, we can directly generate the test vectors. Okay? Fine. So, in general, for a 2 to the power n to 1 line multiplexer with n select lines, we need 2 to the power n plus 1 test vectors. Here this n was 2, that is why we need 2 to the power 3 equal to 8 test vectors. And in this scheme, all the functional faults can be detected. Like what are the functional faults we are talking about? That some input line is incorrectly selected, as I had said, or you may check some of the line they are permanently fixed at 0 or 1. So, whatever you are applying from outside, instead of that value, it is always at 0 or always at 1. Some line may be accidentally short circuited, or you are connecting, it is not connected, it will treat as 0 maybe. Okay? Because of those kind of failures, this kind of faults can occur. So, this example shows that functional fault model can be very effective, and once you have a functional fault model, you can have a very efficient way of generating the tests. But again, whatever we talked about for a multiplexer, you cannot apply it for an adder. For an adder, the logic and the behavior will be entirely different. So, these techniques are very specific to blocks, all right. So, these are not general. So, let us now look at structural level fault models, which are more common. So, structural level means we view this circuit as a netlist. Netlist means some basic blocks and their interconnections. Typically, the blocks are considered as gates or flip flops. For combinational circuits, it will be only gates. For sequential circuits, there will also be flip flops and their interconnection. Let us say I have a circuit like this. So, the structural fault model that we are talking about, it rests on a very important assumption. The assumption says that the gates or the blocks, they are fault free. There cannot be any fault inside the blocks. Rather, faults can be there in the interconnection lines. So, all the interconnection lines, there can be faults only there. But you may argue that why this kind of assumption? There can be fault inside the gate also. But the logic is, there can of course be a fault inside a gate, but you think the fault may be such that because of that one of the inputs is permanently being treated as if it is at 0. So, you abstract it in a way that the gate you are assuming to be fault free, but that input you are saying that it is permanently at 0. This is the kind of fault you are talking about. Now, although it seems to be overly simplistic, but this has been found to be very effective and it can cover a very large percentage of the actual physical faults, right. Now, we shall be discussing one very popular structural level fault model, which is called the Stuckert fault model, which is widely used in the industry also. Let us see what is the Stuckert fault model. In the Stuckert fault model, the basic assumption is like this: we assume that because of the failures or faults, some of the circuit lines are permanently fixed at either logic 1 or logic 0, and we call them as Stuckert 0 or Stuckert 1 fault. The faults are denoted like this: A Stuckert 0, SA 0, or in short we can also write like this: A/0, or A Stuckert 1, or in short I can write A/1. Okay. So, suppose this is one line of the circuit, I can say that there can be a fault A Stuckert 0, there can be a fault A Stuckert 1, all right. Now, there is another important point also: fan out stems and fan out branches are considered as separate lines. Like you consider this F, F1, F2, this is a fan out stem and these are the fan out branches. Let us try to understand why this is so. You see, this F1 can be connected to some other gate, this F2 can be connected to some other gate, right. Now, you recall that in this fault model we are assuming that these gates are free of faults. Faults can only be there in the interconnections. Now, suppose there is a fault in this first gate because of which the output is always at 0, like F stuck at 0. Now, this fault will equally affect F1 and F2 because the value of F is going to both F1 and F2. But imagine that there is a fault in this gate, because of which this line, let us call it F1, this F1 is stuck at 0. But this fault behavior will exhibit only on, this is not an electrical fault, but because of a fault this gate input is being treated as if it is always at 0. But F or F2 will still work correctly, there will be no stuck at 0 fault in F or F2. Because of this, when you count the number of lines, fan out stems and fan out branches are considered as separate lines. Just remember this. Okay. First, let us talk about single Stuckert fault, which is the most widely used Stuckert fault model. This assumes that only one line of the circuit has a Stuckert fault at any given time. If a circuit has k number of lines, So, each of the line can have two faults, stuck at 0 or stuck at 1. Because only one of them is occurring at a time, total number of faults will be 2k. Let us take a gate level netlist here. This is the NAND realization of the XOR function. You see, here there is a fan out and here also there is a fan out. You count the number of lines 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So, k is 12. Because k is 12, total number of single stuck at faults can be 2k or 24. Okay? Simple. Now, people have also talked about multiple stuck at faults, which means more than one lines having stuck at faults at the same time. So, here something is mentioned that for a circuit with k lines, total number of multiple stuck at fault can be 3 to the power k minus 1, but how it is coming 3 to the power k minus 1? You just imagine like this circuit has k number of lines. Think of each of the individual lines one at a time. Say the first line, it can be in 3 different states. It can be stuck at 1, it can be stuck at 0 or it can be good fault free. The second line can also be in one of 3 states, stuck at 0, stuck at 1, fault free. So, all k lines can be in 3 states each. So, if you look at all possible combinations, it will be 3 multiplied by 3 multiplied by 3 k times 3 to the power k. Okay. And out of this 3 to the power k, there will be one combination which says all of them are fault free. So, you subtract that one. So, it becomes 3 to the power k minus 1, right. So, for the same example, there are 12 lines. You see multiple stuck at faults 3 to the power 12 minus 1 becomes about 5.3 lakhs. So, just imagine for this very small circuit with 4 gates, the number of multiple faults is becoming 5 lakhs. So, what about a large gate with large circuit with 1000 gates or more? Okay. So, counting multiple stuck at faults may become impractical. That is why most of the people they concentrate on single stuck at faults only. Okay. Fine. Now, let us look at some examples of single stuck at fault testing. You think of a single 2 input AND gate. So, there can be 6 faults, A stuck at 0, A stuck at 1, B stuck at 0, B stuck at 1, F stuck at 0, F stuck at 1. So, I am showing the set of tests that can detect all faults. So, I tell you 0 1, 1 0 and 1 1 are sufficient. 0 1, if we apply 0 1, then under fault free condition output will be 0. So, if either A stuck at 1 fault is there, then 1 1 will come, the output will change to 1, it can be detected, or output F stuck at 1 fault is there, then also output will become 1, it can be detected. Similarly, 1 0 can detect B stuck at 1 and F stuck at 1, and 1 1, if we apply both 1, let us say 1 and 1, so output is supposed to be 1. So, if there is a fault A stuck at 0, that can be detected because one of them is becoming 0, output will becoming 0. The second one B stuck at 0 can also be detected, that will also change, and third one this F stuck at 0 can also be detected. So, you can detect a fault if the fault free output and the faulty output, let us call F alpha, they are different, which means their exclusive OR is equal to 1. Exclusive OR equal to 1 when they are either 0 1 or 1 0, means they are different. This is the necessary condition for the detection of a fault. Okay. Take a larger AND gate, 4 input AND gate. Following a similar logic, you can see this, you can verify that you require only 5 test vectors for testing all faults. 0 1 1 1, this will detect only A stuck at 1 and F stuck at 1, 1 0 1 1, B and F, C and F, and this one D and F. But 1 1 1 1 will detect all the stuck at 0 faults. So, these 5 test vectors taken together can detect all the 10 faults, right. Let us take some more example. Let us take a 3 input exclusive OR gate, 3 input XOR gate. So, I am saying that 2 test vectors are sufficient. Why? Let us say you apply 0 0 0, the output is 0. The property of an exclusive OR function is that whenever one of the input changes, the output also changes. So, if the first one changes from 0 to 1, that means there is a stuck at 1 fault, it will be detected. Second line stuck at 1 fault, that will also be detected. Third one stuck at 1, that will be detected, and output stuck at 1, of course, it will be detected. Similarly, for 1 1 1, if we apply 1 1 1 in the input, the output will be 1. So, any stuck at 0 faults will make the output 0. So, these 2 test vectors are sufficient. But for a 4 input XOR gate, 4 means in general for an even input XOR gate, this will be true for any odd number. Like for an m input XOR gate, well, if it is odd, you need only 2 test vectors like this, all zeros and all ones. But you have even number of inputs, then you will be needing 0 0 0 0, but the output is 0. This will detect all stuck at 1 faults in the input and also stuck at 1 in the output. But if we apply 1 1 1 1, for that also even number of 1, that also output will be 0. This will detect all stuck at 0 fault in the input, stuck at 1 fault in the output, but only stuck at 0 fault in the output is missing. For that, you have to add another test vector, any test vector with odd number of 1s, which will make the output 1, that can detect a stuck at 0 fault in the output. Okay. So, for an XOR gate, if the number of input is even, you need 3 test vectors. So, these examples illustrate that in the process of test generation, number of test vectors can be drastically reduced. Okay. So, even for a 4 input XOR gate or a 100 input XOR gate, you need only 2 or 3 test vectors. Okay. So, these are some very simple examples to illustrate. Now, there is one other thing I want to talk about, the problem of reducing the number of faults. Like there are some properties that we shall be talking about, 2 properties called fault equivalence and fault dominance, that can actually reduce the number of faults we need to consider in a gate. Okay. So, let us take some examples, it will be clear. First, let us talk about fault equivalence. Well, I am taking a couple of examples, others you can verify similarly. You think of an AND gate. Let us say inputs are A, B, output is F. So, if there is a fault A stuck at 0, what will happen? So, one of the input is always at 0. So, the output F is always 0. If there is a stuck at fault B stuck at 0, then also output is 0. So, if there is the fault output F stuck at 0, then also output is 0. So, you cannot distinguish between these 3 faults, they are equivalent. Okay? So, the idea is that when you are counting the number of faults, you are counting A stuck at 0, B stuck at 0, F stuck at 0 3 times, but you can delete 2 of them if you want. What I am saying is that you can delete 2 of them, you can only keep A stuck at 0 because these 3 are equivalent, and you only generate a test vector that can detect A stuck at 0 fault, which is 1 1, output is 1, and this test vector can also detect B stuck at 0, F stuck at 0 automatically. Similar is the case for the other gates you can verify. For a NAND gate, the input stuck at 0 and output stuck at 1 are equivalent. For an OR gate, all stuck at 1 faults are equivalent, input stuck at 1, output stuck at 1, they will all make the output F equal to 1, okay, like this. Now, this kind of a thing, that when there are a set of equivalent faults, you keep one, delete the others, this is called equivalence fault collapsing. Let us take an example. Let us take a circuit like this. There are some AND gates and OR gates only we are considering. Okay. These are fan out stems, so the stuck at 0 and stuck at 1 faults will be different. For this AND gate, as I have said, the stuck at 0 faults are all equivalent. So, these let us say these 3 faults are equivalent, stuck at 0 in the first input, stuck at 0 and stuck at 0. So, using fault collapsing, what I is saying, I keep only one, other 2 I delete. The red ones are the ones I have deleted. Similarly, for the second one, I keep this, I delete this stuck at 0 and stuck at 0. Third one, I keep this, I delete this, I delete this. For an OR gate, the stuck at 1 faults are equivalent. So, I keep only one stuck at fault, I delete this, I delete this. Here, I keep this, I delete this, I delete this. For the last AND gate, I keep this, I delete this, I delete this. So, how many I have deleted? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, in the original circuit, number of faults were 32. Okay? And after deletion, so I have removed the red marked ones, I am left with 20. This is what is meant by fault collapsing. After fault collapsing using equivalent faults, I am able to reduce the number of faults. Okay? This is one technique, and the other technique is called fault dominance. Okay, fault dominance, let us try to understand the definition, then we will take an example. This says, if all the tests for some fault, let us call the fault is F I, also detects another fault F j, then we define that F j dominates F I. We denote it like that, F j arrow F I. So, I have an example I will show, like output stuck at 1 for an AND gate dominates input stuck at 1, but whenever such a dominance relation is there, we will keep F 1 and we will be deleting F j, we will keep F I, we will delete F j. This is called dominance fault collapsing. Well, this may look a little confusing, let me take an example to explain this, this will be easiest. Let me take an example. Consider a 3 input AND gate, okay, and you take the 2 faults F I and F j as follows. F I is stuck at 1 fault in one of the input A, let us say A is stuck at 1, this is my F I call this as F I, and F j, let us call this stuck at 1 in the output F stuck at 1, this is my F j. Now, for this AND gate, you see, for F I, what are the tests you can use? For testing for A stuck at 1, there is a single test vector 0 1 1 0 1 1, because under fault free condition F will be 0, if there is a stuck at 1, the output will be different. So, it will be detected. But for output F stuck at 1 fault, there can be many test vectors possible. So, any test which makes the output 0, that will be a test for f j, because normally output will be 0, f stuck at 1, output will become 1. Out of these you see 0 1 1 is also there. So, what I am saying, if such a pair of faults are there, you remove f j from the list, because if you keep f I, this 0 1 1 test will be included anyway, and 0 1 1 is also a test for f j. So, f j will also get detected. Okay. This is the idea behind dominance fault collapsing. You keep f I, you delete f j. Okay. So, remove f j and keep only f I, because if you detect this f I, it will automatically also detect f j. So, with this we come to the end of this lecture, where we have briefly covered the problem of fault modeling, and we have looked at some of the very you can say important and commonly used fault models. We looked at one of the functional fault model for multiplexers. Then we talked about the stuck-at fault, both single and multiple. So, we shall be continuing our discussion in the next lecture, where we shall be talking about the problem of test generation. Thank you.